We're on to our first topic of Unit 3, Area of Study 2 now, which is food, fuels and energy systems. And the key knowledge that we need to cover in these lessons are looking at fuels, both chemical and food fuels, so carbohydrates, fats, proteins, phosphocreatine, ATP, and how they're used to resynthesize ATP during physical activity. Looking at the characteristics and interplay between our three energy systems. So we've got our two anaerobic energy systems, the ATP-CP, also known as the ATP-PC system, anaerobic glycolysis, and our aerobic energy system. So looking at the interplay between those three during physical activity, the rate in which they produce ATP, the capacity in which they can sustain exercise, and how their contribution changes in relation to exercise intensity and duration. And that sort of addresses that bottom point there too, looking at the relative contribution of energy systems and fuels used to produce ATP in relation to the exercise intensity, duration and type. When we talk about fueling muscle contractions in the body, we're really talking about the use of ATP to fuel muscle contractions. Everything in the body really comes back to our ability to make ATP. So earlier in the course when we talked about our acute responses to exercise, well, a lot of those responses in the cardiovascular, respiratory and muscular systems came about because we needed to be producing more ATP because our muscles needed to use more ATP. And that's because ATP, if I could say it any more times, is the only direct chemical fuel source that will fuel muscle contractions. It doesn't matter what food you eat, we do not use the energy from food directly to fuel muscle contractions. We use ATP. The reason we eat is because we use the energy stored in the food we eat to be broken down so that we can release that energy because we need that energy to make ATP. And then the ATP is used by the cells. Problem with ATP is we don't have a lot of it in our body, so we really store only a pretty small amount, enough to fuel max intensity exercise for 2 to 3 seconds. So if you got up and just started sprinting, all of your stored ATP would be gone within 3 seconds. The good thing is our body is really good at resynthesizing ATP, and pretty much as quickly as we break it down, we can build it up again. And we use our energy systems to make ATP. So we've got our aerobic energy system, the one that uses oxygen to make ATP. And then we've got a couple of anaerobic systems which give us the ability to make ATP even when we don't have enough oxygen coming into our body. And those anaerobic systems are our ATP-PC system and our anaerobic glycolysis system. Let's have a little look at this diagram here to see how ATP actually works. So if we look at the top, that is our ATP molecule. We have one molecule of adenosine, which is the big A. Then we have 1, 2, 3 phosphates. Now, energy is stored in every chemical bond, but this bond here between the second and third phosphate is a high energy bond, and there's a lot of energy stored within that bond. What we do is our cells are able to break off that last phosphate from adenosine triphosphate, as you can see here. So the phosphate is released, and by breaking off that last phosphate, we release the energy that was stored in the bond, and we can use that energy for muscle contractions. What we're left with is the adenosine, but now it only has 2 phosphates, so we call it adenosine diphosphate, and we want to resynthesize that molecule back into ATP so we can use it again. So what we want to do is we want to get the phosphate that was on its own, and we want to join that back to the end of the second phosphate so that we get back to adenosine triphosphate. For us to be able to attach the phosphate back on, we need an input of energy to enable us to do that. And that energy is coming from our food. That's why we eat. So when I say we use the energy from our food to make ATP, essentially we use the energy from our food to enable us to have enough energy to join the third phosphate back onto ADP. Once we do that, it's ATP again, and then it just keeps working in a cycle over and over. So our energy systems, the aerobic energy system, ATP-PC system, anaerobic glycolysis, they're systems that break down food to release energy so that we can attach the third phosphate back onto any ADP molecules. So, as I said before, our main foods that we use to produce ATP are our carbohydrates, our fats, and our proteins. And we've got a bit of terminology to do with these that sort of you'll come across while you're talking about your energy systems. And some of the words they use interchangeably, and some of them you need to pick to use the right word at the right particular time. So if we have a look going across the top row to start with, so if we look at carbohydrates as one of our food fuels, which we would know has things like breads and pastas and rice that we eat. Carbohydrates, when they're in your body, they get broken down in your digestive system, and then your body stores them in the form of glycogen. So glycogen is a type of carbohydrate. It's sort of a more chemical science type name for our carbohydrates. So we store carbs in the form of glycogen, and we store glycogen in our liver and in our muscles. So when you eat your carbohydrates, they get broken down, they travel around your blood, and they go to our storage sites, which is our liver and our muscles. Now, the carbohydrates, or the glycogen, it gets broken down as we need it, and it gets broken down into what we call glucose. So glucose is a small single molecule, a single sugar molecule, and many glucoses form together in a chain to form glycogen. So in the liver and the muscles, as we need to produce more ATP, the glycogen would be getting broken down into individual glucose molecules. They get released into the bloodstream, and then the glucose molecules travel through the bloodstream and they go to the cells that need to use them to undergo cellular respiration, we call it, which is the process to produce ATP. In terms of our fats, our chemical name for them is triglycerides, and triglycerides are stored in your body in your adipose tissue, which is your fat tissue, and they're also stored to a degree in your muscles. Just like glycogen, when your body needs to use the triglycerides as an energy source to synthesize more ATP, the triglyceride, which is composed of a glycerol molecule and 3 fatty acids, it gets broken down and it releases its free fatty acids into the bloodstream, and they travel around the bloodstream, and then they will go and be transported into the cells that need them so that they can make more ATP inside that particular cell. As for our proteins are found in our body in the form of amino acids. So an amino acid is a small molecule, and lots of amino acids get joined together to make a protein. Where do we store our amino acids in our body? We store them in our muscles. And when the body needs to release some of that protein, the amino acids are released into the bloodstream, they travel around the body, and they go to their target cells to be used for ATP synthesis. Though it is important to note, when we're looking at our energy systems, we really don't use protein to make ATP. We can technically, and we do in extreme situations like an ultra marathon where all the other fuels have been completely exhausted. But your body typically does not use proteins as a main source of making ATP. We more use proteins and amino acids to build muscle. Under proteins, I've also got creatine phosphate listed. Now, your body can make creatine phosphate, but you can also get some creatine phosphate from the intake of your proteins. And creatine phosphate is a chemical found in your body, stored in your muscles, and transported around the body in that form of creatine phosphate. And cells can use creatine phosphate just like they could use glucose, just like they could use fatty acids, to be broken down to produce more ATP. What we're going to talk about in the next few slides is which fuel source do we use at which particular time, because they all vary in terms of how quickly they can be broken down to produce ATP. So obviously high intensity exercise requires ATP to be produced really fast, so you're going to pick the food fuel that can be broken down to produce ATP the quickest. So it's a process really. You start with your large molecules, your carbohydrates, your fats, your proteins. You break them down into their smaller molecules, glycogen, triglyceride, amino acids. You store them, and then eventually you break them down further, glucose, fatty acids, amino acids, creatine phosphate, and then them themselves are broken down even further to produce ATP. Carbohydrates are by far the body's preferred food fuel during exercise. So anything in short duration that's max intensity, typically over about 5 seconds. 5 seconds and under, phosphocreatine is going to be predominant energy system. But 5 seconds and over, particularly things like your 400-meter run, your carbohydrates are most definitely your preferred fuel source, and they would be contributing the most. Also, for extended endurance events, at a high-ish intensity, so say over 65% of your max intensity, carbohydrates remain the preferred fuel source. Low intensity exercise below 65%, your fats would be your preferred fuel source, but as soon as you get over that 65%, it's definitely your carbs. So carbohydrates are used to fuel both almost all of your energy systems really. So they're directly used to fuel the aerobic energy system to get broken down to make ATP. They're also used directly in the anaerobic glycolysis system to get broken down to make ATP. But they also need to be present for the ATP-PC system to work to produce ATP. So they're pretty vital. As I said before, they're stored in the liver and the muscle cells as glycogen. When your body needs them, they get broken down into glucose, which is a simple sugar. That gets released in your blood. That travels to a cell, enters the cell, and then gets broken down in the cell to make ATP for that particular cell. Some examples of carbohydrates. You might have heard before the word complex carbohydrates and simple carbohydrates. It's to do with their chemical structure and how long they take to digest and break down. Your complex carbohydrates are things that are slow energy releasing, that takes the body longer to break them down to produce ATP. Whereas your simple carbohydrates, they're things that are typically, almost instantly broken down into glucose. So they enter your bloodstream really quickly and they make ATP quite quickly, but they're not slow releasing. So you get that lull after your sugar high, you sort of hit the wall. When we talk about fats as a fuel source, typically we say they're our preferred fuel source at rest. And I know I said on the last slide there at low intensity exercise as well. And they also become a pretty important food fuel during submaximal exercise that lasts several hours. Now that is always dependent on how much carbohydrate is being put into that athlete's body before an event, or whether they're replenishing their carbohydrate supplies during the event. The reason we would say it's important in submaximal exercise that lasts several hours is because you would assume after several hours an athlete's carbohydrate supplies will have depleted significantly, and there won't be enough carbohydrate in their body to be the preferred fuel source anymore. And if they wish to continue exercising, then the body needs to look for another fuel source, and then it would look for fats. Why would it look for fats? Because we have a lot more of it in our body. We would have more fat in our body than carbohydrate, and fat is a more energy rich molecule. You can yield a lot more ATP from one triglyceride than what you can get from one glucose molecule. So fats do supply us with more energy. So if you ever get a question that says which is the most energy rich molecule, it's definitely your triglycerides, your fats. The problem is, firstly, they can only be broken down during your aerobic energy system. So for high intensity exercise where you're using your anaerobic system, fats are no good. They can't be used to make ATP. But during aerobic activity, they definitely can be used to make ATP, but it's a pretty slow resynthesis of ATP. We need a lot of oxygen to break down fat in comparison to carbohydrate, and it takes more time to break down fat in comparison to carbohydrate. So when you're exercising at an intensity of 65%, your max exercise intensity or above, you don't really have the time to break down the fats because the demand your body is putting on itself to be supplied with ATP is at the level where carbohydrate breakdown is really the only thing that can produce the ATP fast enough. If you get several hours into a marathon, for example, and your carbohydrates have depleted, and then you switch to using your fats, well, that coincides with your performance slowing as well, because your body's no longer going to get the ATP as quickly because it's not making it as quickly because it's not making it from carbohydrate anymore. It's making it more predominantly from fat, and that's why an athlete would slow down. Our final food fuel being proteins. As I said at the start of this presentation, yes, it can technically be broken down to produce ATP, but does the body do it very often? No, not really at all. So the protein can be broken down into the amino acids, travel through the bloodstream, and can be used by cells to be broken down further to make ATP. But your body would only do that if your carbohydrate availability is really low, and also if your fat fuels are really low as well. So if you're looking at this example over here of the ultra marathon, an event that can go for 72 hours, that is an extremely long duration aerobic event. And getting towards the end of an event like that, you will have depleted a lot of your carbohydrate supplies, a lot of your fat supplies, and if you're going to continue to be producing ATP to exercise, that's when your body might turn to breaking down your proteins. Breaking down your proteins takes a lot of oxygen, even more oxygen than breaking down your fats. So it would also coincide with a significant decline in performance. And more so than talking about proteins as a food fuel, we typically more look at them as a fuel that helps us to build muscle and repair muscle. So this brings us to our chemical fuel, creatine phosphate. So far we're still talking about something that's broken down to produce ATP. So we've got our food fuels, carbohydrates, fats and proteins can be broken down into smaller molecules for the purpose of releasing energy used to make ATP. And we can also use this particular chemical fuel, which is creatine phosphate. And we can break creatine phosphate down, and from breaking it down there's a release of energy, and we can use that energy to resynthesize our ATP. So it actually works a lot like an ATP molecule. So creatine phosphate is a single creatine molecule chemically bonded with a single phosphate molecule. And much like I talked about how ATP worked earlier, there's energy stored in the chemical bond between the creatine and the phosphate. If we snap off that last phosphate, energy is released, and that energy is used to make ATP. So when do we use creatine phosphate? We use it in max intensity exercise. So you would be able to fuel maximum intensity exercise for about 1 to 10 seconds using creatine phosphate. However, probably after about 5 seconds, it would no longer be the predominant thing fueling exercise. You would have your anaerobic glycolysis. But yeah, we typically say it fuels exercise for about 1 to 10 seconds. So we store our creatine phosphate in our muscles, and it does not need any oxygen to break it down. So that's why we call it an anaerobic energy system. We produce it naturally in our body, in our liver, in our kidneys, in our pancreas, but we can also bring it into our body through some of our proteins, like our beef, salmon, and our tuna. So when we look at how those different fuels contribute to producing ATP during exercise, we look at their contributions, because there's never going to be a time where any one is the single thing contributing to our ATP production. So if we're looking at carbohydrates and fats, even if we're looking at phosphocreatine as well, they're all contributing together at different times. What we look at is what is the most predominant system out of all of those ones that are contributing at any one time. So we say the predominant energy system. If we look at fats and carbohydrates, which is what this graph down the bottom here is looking at, what you can see is on the vertical axis here is our percent contribution to the total energy, and on the bottom axis we've got different exercise intensity. So 0% all the way up to working at 100% max exercise intensity. You can see that at rest, fat is contributing significantly more to our production of ATP. And what we would say is at rest, fats contribute about 2/3 of the food fuels for making ATP, whereas glycogen is still contributing, but it's only contributing about 1/3. As exercise intensity increases, carbohydrates increase their contribution to our energy systems. So as we get to 20% exercise intensity, fats is still the most, but carbohydrates has increased since rest. Go up to 40, up to 60, and at about 60% exercise intensity, this is where fat and carbohydrate contribution cross over. So we could say at 60% exercise intensity, according to this graph, it's an equal contribution by fats and carbohydrates to energy production in the body. As soon as, so that trend continues to increase as with maximum intensity increasing, so exercise intensity increasing, carbohydrate contribution continues to increase. So as soon as we step up over 60%, you can see that carbohydrate contribution from that point on surpasses fat contribution, and the contribution of the fats goes down. So why does it go down? Because we still need to produce the same set number of ATP, but if we're producing more of it with carbohydrate, well, there's less of a need there for producing it with fat, so it decreases to maintain a balance. In terms of this table down the bottom here, you can see, as I said before, if we're comparing fats, triglycerides, to carbohydrates, glycogen, the triglyceride is a far more energy-rich molecule. So from one single molecule of triglyceride, you're able to make 441 molecules of ATP. However, from one single molecule of glucose, you're only able to make 36 ATP. So carbohydrates produce far less ATP. However, during exercise, they're still the body's preferred energy source. Why? Because for fats, you need a lot of oxygen. For carbs, you need less oxygen. For fats to produce that 441 ATP, it's going to take a long time. It's a slow production of ATP. Carbohydrates, it's a really fast production of ATP. And that speed varies depending on your system. So ATP PC, incredibly fast supply of ATP. Anaerobic glycolysis, really fast supply of ATP. Anaerobic energy system is a slower supply of ATP compared to the anaerobic ones, but is still significantly faster than our ability to produce ATP by breaking down triglycerides. Good old human nature loves looking at natural processes in the body and ways of manipulating them to improve our performance. And when we talk about food fuels, it's really no different. So one way athletes would manipulate their ability to produce ATP is through something we call carbohydrate loading. And I'm sure you've probably heard about it before. Prior to a significant event, people like to carbo load. Now, for that to be effective, you would want the event to be decent in intensity and a decent length of time in duration. But nonetheless, you can carbo load. So what is carbo loading? It's loading up your body with an increased consumption of carbohydrate. So 3 to 5 days before a competition, you would be significantly increasing the amount of carbohydrate you're eating. And at the same time, you would be tapering your training load. So by tapering your training load, you would be burning less of the carbohydrate. By increasing your carbohydrate intake, you would be storing a lot more glycogen in your body. So by the time you get to competition day, you have significantly more glycogen stored in your body than what you would have had if you didn't purposely carbohydrate load. Why would you do that? Well, as we sort of said before, ATP is produced the quickest when glycogen is our preferred fuel source. So the longer we can delay our body shifting to using fats as our preferred fuel source, the longer we can perform at a higher intensity, because the longer we can perform where we're producing ATP really quickly. So by carbo loading, it's going to take your body, well, you're going to be able to exercise for longer before you get to the point where you've broken down most of your glycogen supply, and then where your body needs to shift to fats. So the benefit is you can perform at a higher intensity for longer. The disadvantage is you probably could get some gastrointestinal discomfort because you're needing to digest all of that carbohydrate you've eaten, and you're going to put on some body weight because you've decreased your training and you've purposely increased your carbohydrate intake. So sometimes in an event where body weight is going to play a role, you're shifting a greater weight around the course or whatever the event is than what you would have if you didn't carbo load. Another way we can manipulate the use of our food fuels is through something we call glycogen sparing. Now, this has nothing to do with your dietary intake, and there's no way you could choose to do this. This more comes as a result of an endurance athlete developing some chronic adaptations from all of their aerobic training. So, as we said earlier, up until about 60% of exercise intensity, or close to 65, fats are the main food fuel being used to produce ATP. And then after about 65% of max intensity exercise, glycogen is contributing the most to the production of ATP. Now, what we see in elite endurance athletes is that they're able to prolong the point in which they start using glycogen as their preferred fuel source. So by doing that, they're extending the period of time in which they can use triglycerides as their preferred fuel source. So they could be exercising above 65% of max intensity and still be using triglycerides as their preferred fuel source. What enables them to do it is essentially the fact that through their training they've developed more mitochondria in their cells, and they're better at using fats more efficiently to produce ATP at a decent rate, where they can use that to sustain exercise above those intensities. What's the benefit of it? Well, it delays or prevents hypoglycemia. So hypoglycemia is the point at which your glycogen stores have depleted and you're going to shift to fats as your fuel source. And that's the point post hypoglycemia where you would see a decent decline in performance because you can't produce ATP as quickly. If you are using triglycerides longer whilst you're exercising at higher intensities, you're sparing your glycogen because you haven't started using that as your preferred fuel source yet. So you're saving it. There's more of it stored in your body. So as you continue into that endurance event, you're going to prevent the point, well, you're going to delay the point in which hypoglycemia sets in because you've delayed the point at which you start breaking down your glycogen stores. So you're going to have more glycogen to call upon later in the race. Therefore, you would be able to perform at a higher intensity for longer, which you'd see being particularly useful when you get to the end of the race.